Hi everyone. So we'll continue again with the first lecture this semester, the first real lecture, which is an introduction to computers, programs, and Java. So this will contain a little bit of programming towards the end. We'll learn how to write a simple program, but mostly it will be an overview of what is required for a computer system to work, what are the parts of a computer. That includes smartphones, tablets, or any kind of devices that you may own. So what is a computer? Basically, a computer consists of the CPU, central processing unit, main memory, which is volatile memory that has very high speed, but basically which will be erased the moment that you restart your device. Hard disk or any kind of external storage or internal storage for a long period of time that will stay the same even if you restart the device. The monitor or the screen, any output devices like printers, any communication devices like network card, input devices like keyboard, mouse, touch screen, and everything stands on a single bus. This bus is basically the main communication line between all of these devices: CPU, main memory, storage, communication devices, input devices, and output devices. Sometimes some devices can be both input and output, like touch screens. They are output devices, like the monitor, but they also basically are input devices through the touch. So we start with the main important part in the computer, which is the central processing unit, the CPU. This CPU, this part of the computer, will retrieve instructions from main memory and execute them. The CPU speed is measured in hertz, or which are basically cycles or instructions executed per second. You will see speeds of CPUs represented in megahertz and gigahertz. Basically, these megahertz are 1 million instructions per second or 1 million pulses per second. Gigahertz are 1 billion pulses per second. The main memory stores both your data and the program instructions for the CPU to execute. There are ordered sequences of bytes, 8 bits or 1 byte, binary unit base. Everything on a computer is stored in binary, 0 or 1s, because all of the electronic devices that we have today are efficiently implemented if they store, if there exists information or not into a location. So the number system used by computers is the binary number system, is different than the decimal number system that is used by humans. Like for instance, the number 10 in decimal is the number 1010 in binary. It's basically a number system in which for every decimal location or any location there exists only 0 or 1 that can be stored. So how is data stored on a computer? It's using binary, a base 2 number system. At every location it can store if there is information like 1 or not in that location. Humans are using base 10. And the reason for that is that we have 10 fingers, basically our hands have exactly 10 fingers in total. And when we started in prehistoric times to count our belongings, like how many sheep do we have, how many other houses do we have, other objects, we use the number of fingers that we had. Like we have 10 sheep, we have 9 sheep, we have 8 sheep. And then when we wanted to say 24 or any number that is bigger than 10, we basically have 2 digits. 2 and 4, basically 24. Computers like binary, and the reason why is that it's easier and more cheaper to make hardware that stores and processes binary numbers like 0 and 1. The transistor, which is basically the basis for integrated circuits, is basically an electronic device that can store, if there exists information 1, or doesn't exist information at that location, or 0. So it's more efficient for computers to do binary numbers. So the entire memory of a computer, and in fact the way that the CPU executes instructions, is done in binary. You may actually see in code, when we write code, these kind of binary numbers like 0, 1, 0, 0, 1, 0. It's a number in binary that represents a number that can be represented also in base 10, in decimal, or can be represented in hexadecimal, and so on. Moreover, if we want to store characters, like for instance J, A, V, A, or any other character in an encoding, we have basically to encode that character as a number and then store it in binary. So there exist encodings or mappings between characters and numbers. The one that is used in Java is Unicode, and the encoding scheme for that Unicode is UTF-16. Basically, the size of a character by default is 16 bits or 2 bytes. Every location in memory is addressable. These locations must be slices of 8 bits, basically, which is 2 to the power 3. Here you can see that we can access the location at index 2000 is basically 8 bits, 2001 is 8 bits, and so on. So the first thing that we are going to talk about actually in this class is number systems. Number systems are basically implementations of numbers in different systems that have a different base. Basically, the number of digits in that number system is for binary 2, for octal 8 bits, or 8 characters to symbolize basically the 8 numbers in that number system. For decimal we have 10, we have digits from 0 to 9. For hexadecimal, which is a base that a base with 16 digits, is from 0 to 9, followed from A to F. So in total 16 different digits. So as I said, computers use binary numbers internally because devices like memory and disk are made to store 0 and 1s. A number or a text inside the computer is encoded into a sequence of 0 and 1s. Binary numbers are not intuitive for humans, for us, because we are using decimal numbers in our daily life. When you write a number like 20 in a program, it is assumed to be a decimal number. It means digit 2 multiplied with 10 to the power 1 plus digit 0. So in total it's basically 20. Internally, the computer must convert any decimal into binary and vice versa when it outputs that number to us on an output device. So let's start with the basics. Basically, the type of number system that we are using in our daily life is the decimal number system. We have digits from 0 to 9 to represent basically values from 0 to 9. A decimal number is represented using a sequence of one or more of these digits. The value of each digit in that sequence represents the number multiplied with the base to the power of that in that position. The positions start from the right hand side with 0, and then we increment with 1 for every position from right to left. A position in the sequence has a value that is an integral power of 10. For instance, when we have a number like 7423, it represents 7 multiplied with 10 to the power 3 plus 4 multiplied with 10 to the power 2 plus 2 multiplied with 10 to the power 1 plus 3 multiplied with 10 to the power 0. So basically it's 3 multiplied with 1 plus 20 plus 400 plus 7,000, which is 7,423. The same system is applied for any number system. So when we will see binary, we'll have a sequence of such binary digits, which are called bits, and we start with the rightmost one as 2 to the power 0 multiplied with that bit, plus 2 to the power 1 multiplied with that bit, and so on. So we started with the decimal number system because the decimal number system is familiar to all of us. We say in this case that the number system base is 10 or radix for the decimal number system. Similarly to that, the base for the binary number system is 2, since the binary system has 2 digits, and the base for the hex number system or hexadecimal is 16, since the hex number system has 16 digits. So let's see, for instance, binary numbers. Binary numbers are quite long. Basically, if we want to represent a number, which basically is represented here, 10, 10, 10, 10, 10, 10, it's quite long to read it, to write it, and so on. Therefore, for most programming systems, we actually represent binary numbers into hexadecimal. Hexadecimal are a number system in which every 4 bits in the binary system corresponds to 1 digit in the hexadecimal system. So 1010 stands for 1 multiplied with 2 to the power 3, which is 8, plus 1 multiplied with 2 to the power 1, which is 2. That is 10. 10 corresponds in hexadecimal to the letter A, to the digit A, because they wanted to use one single character for every digit in the number system. So they used from 0 to 9 to represent basically hexadecimal numbers from 0 to 9, but then they used 10, they used A for 10, B for 11, and so on up to 15, F for 15. So you will see different number systems throughout the programming in this class. You will see binary, you will see decimal, which you are familiar with. You will also see hexadecimal numbers, which have 16 digits, and these digits are from 0 to F. The letters from A to F corresponding to the decimal numbers 10 to 15. The octal number system has only 8 digits. The radix or base for octal is 8, and the digits that will be used for any number in octal are from 0 to 7. So let's learn about how to convert binary numbers to decimal and vice versa. We'll start with the conversion from binary to decimal. So binary numbers are a sequence of bits or binary digits, and these bits, each bit, it can be 0 or 1. So for instance, if we have a sequence of bits, we can also label these bits with the position starting from the right hand side with the index 0. So the rightmost digit has the index 0, the second digit 0 or 1 has the index 1, the next digit has the index 2, and so on from right to left. The equivalent decimal value for that binary number is the binary digit at position n multiplied with 2 to the power n plus the binary digit at position n minus 1 in this ordering from right to left starting with 0 multiplied with 2 to the power n minus 1 plus the next binary digit multiplied with 2 to the power n minus 2, and so on up to b0 multiplied with 2 to the power 0. So for instance, if anyone gives you a number 10 in binary, that number corresponds to 1 multiplied with 2 to the power 1 plus 0 multiplied with 2 to the power 0. But 0 multiplied with anything is 0. So in this case, this will be equal with 2 in decimal. So 10 in binary is 2 in decimal. Similarly, 1010 in binary corresponds to 1 multiplied with 2 to the power 3 plus 0 multiplied with 2 to the power 2 plus 1 multiplied with 2 to the power 1 plus 0 multiplied with 2 to the power 0, which is 0. So this is 8 plus 0 plus 2 plus 0, which is equal with 10 in decimal. Let's take another number in binary, 10, 10, 1011. We want to convert it from binary to decimal. First thing, we are going to label each digit with the position starting from the right hand side with the position index 0. So first, the digit on the right hand side has index 0, next one has index 1, next one has index 2, 3, 4, 5, 6, 7. So this number in binary is 1 multiplied with 2 to the power 7 plus 0 multiplied with 2 to the power 6 plus 1 multiplied with 2 to the power 5 plus 0 multiplied with 2 to the power 4 plus 1 multiplied with 2 to the power 3 plus 0 multiplied with 2 to the power 2 plus 1 multiplied with 2 to the power 1 plus 1 multiplied with 2 to the power 0. So that will be equal with 128 plus 2 to the power 5, 32, plus 2 to the power 3, that's 8, plus 2 plus 1. That sums up to 171 in decimal. It's very useful to remember the powers of 2. So basically 2 to the power 0 is 1, 2 to the power 1 is 2, 2 to the power 2 is 4, 2 to the power 3 is 8, 2 to the power 4 is 16, 2 to the power 5 is 32, 2 to the power 6 is 64, 2 to the power 7 is 128, 2 to the power 8 is 256, 2 to the power 9 is 512, 2 to the power 10 is 1024, and so on. You remember them after you use them for a long time because it's very important to know binary numbers. Now, next is how do we convert from decimal to binary? The conversion from decimal to binary is basically to find for any number d in decimal the corresponding unique representation in binary bn to b0 such that the number d is equal with bn to multiply with 2 to the power n plus bn minus 1 multiply with 2 to the power n minus 1 and so on up to b0 multiplied with 2 to the power 0. In such a way that bn is 1 and all of the other digits bn minus 1 to b0 are either 0 or 1s. It's easy to prove basically prove by contradiction that there is a unique representation and there is always a representation of such a sequence of bits that represents the decimal number d. These numbers can be found successively dividing by 2 the original digit until the quotient of the division is 0. So the remainders will be basically obtained in reverse order of the division from bn to b0. So let's start with the number 123. You see the number 123 is on the right hand side. We divide it by 2. We get the quotient 61 and the remainder 1. Because 61 multiplied with 2 is 122 and the remainder is 1. We continue with the quotient by dividing it with 2 and obtaining its quotient and remainder. And we continue basically like this. 30 divided by 2 is the quotient 15 and the remainder 0. 15 divided by 2 is the quotient 7 and the remainder 1. 7 divided by 2 is the quotient 3 and the remainder 1. 3 divided by 2 is the quotient 1 and the remainder 1. And 1 divided by 2 is the quotient 2 and the remainder 1. Until we get a quotient that is equal with 0. That moment the conversion is finished, and if we read the remainders in reverse order as we obtain them from right to left, we read them from left to right. That is the binary number corresponding to 123 in decimal. So in our case it's 111111 in binary. You can actually check yourself if you are using the Windows calculator by changing the view of this calculator to the programming or the scientific version of this calculator, and basically entering the number in decimal and then changing the number system to binary. You can also see what is the representation of that in octal and hexadecimal. Before we continue with hexadecimals, which follow exactly the same procedure that we discussed, let's see if there are any questions in the chat. And we can also do a few examples from my programming lab of conversions of number systems. So let's see first if there are any questions. Okay, and let's go to my programming lab. So, my programming lab, I will use my user and password. I will load the summer my programming lab. And let's actually start with Appendix F, number systems. So we are going to start with the first question. The binary equivalent of the decimal number 3 is what? So we take 3, we divide it by 2, we get the quotient 1 and the remainder 1. We know that if we continue this process, 1 divided by 2 gives us the remainder 1 and the quotient 0. So the binary equivalent of the decimal number 3 is 1, 1. Next question. The binary equivalent of the decimal number 6 is what? Again, we basically do it the same way in reverse order. 6 divided by 2 gives us the remainder 0, the quotient 3. 3 divided by 2 gives us the remainder 1 and the quotient 1. 1 divided by 2 gives us the remainder 1 and the quotient 0. We finish at this point, so the binary equivalent of the decimal number 6 is 1, 1, 0. Let's continue with 2. 2 divided by 2 gives us the remainder 0 and the quotient 1. 1 divided by 2 gives us the remainder 1 and the quotient 0. So the decimal number 2 corresponds to the binary number 1, 0. 9. 9 divided by 2 gives us the remainder 1 and the quotient 4. 4 divided by 2 gives us the remainder 0 and the quotient 2. 2 divided by 2 gives us the remainder 0 and the quotient 1. And 1 divided by 2 gives us the remainder 1 and the quotient 0, so we stop. So we obtained 1, 0, 0, 1. Let's submit the answers. And they were all correct. Next question. What's the binary equivalent for the number 5? Again, 5 divided by 2 gives us the quotient, the remainder 1 and the quotient 2. 2 divided by 2 gives us the remainder 0 and the quotient 1. 1 divided by 2 gives us the remainder 1 and the quotient 0. We can also do the reverse transformation to make sure that the answer is correct. 1, 0, 1 stands for 1 multiplied with 2 to the power 2, that is 4, plus 1 multiplied with 2 to the power 0, which is 1. 4 plus 1 is equal with 5. 0 is just 0 in decimal and in binary. Let's go with 14. 14 divided by 2 gives us the remainder 0 and the quotient 7. 7 divided by 2 gives us the remainder 1 and the quotient 3. 3 divided by 2 gives us the remainder 1 and the quotient 1. And 1 divided by 2 gives us the remainder 1 and the quotient 0. 23. 23 divided by 2 gives us the remainder 1 and the quotient 11. 11 divided by 2 gives us the remainder 1 and the quotient 5. 5 divided by 2 gives us the remainder 1 and the quotient 2. And 2 divided by 2 gives us the remainder 0 and the quotient 1. And 1 divided by 2 gives us the remainder 1 and the quotient 0. So 23 is 1, 0, 1, 1, 1. let's also do the reverse, making sure that this is correct. So this is 16 to the power 4 plus 2 to the power 2, that's 4, that is 20, plus 2 plus 1, that is 23. So yes, it is correct. Let's continue. We are going to do everything. The binary representation of an even number, if you look at even numbers, for instance 2 has the representation 1, 0. 4 has the representation 1, 0, 0. Always the last bit for an even number representation in binary ends with a 0. If the number is divisible by 4, it always ends with 2 zeros. Let's see if that is indeed the case. Let's take the numbers divisible by 4. Like for instance, what is the representation of 4 in binary? So the representation of 4 in binary is 1, 0, 0. The representation of 8 in binary is 1, 0, 0, 0. The representation of 12 in binary is 1, 1, 0, 0. It's basically 8 plus 4. The representation of 16 in binary is 1 and 4 zeros. It's 2 to the power 4. So always the last 2 zeros, including from the beginning, from 4, is actually the last 2 digits are 0. So numbers that are divisible by 4 end with 0, 0 in binary. They are both correct. Let's see, the decimal equivalent of the binary number 1 is 1. 1, 0, 0, 0, so it's 1 multiplied with 2 to the power 3, which is 8, plus 0 multiplied with 2 to the power 2, plus 0 multiplied with 2 to the power 1, plus 0 multiplied with 2 to the power 0. Then we have 8 plus 2, basically 2 to the power 3, and 2 to the power 1 is 10. So 1, 0, 1, 0 is the decimal number 10. Let's look at this one. It's 1 plus 2 plus 4 plus 8, which is 15. Okay. Last question. What is 1, 0, 1, 0, 1? So 1, 0, 1, 0, 1 is 2 to the power 0, that's 1, plus 2 to the power 2 for the third digit from the right hand side, that is 4, so it's 1 plus 4 is 5, plus 2 to the power 4, which is 16. 5 plus 16 is 21. Next one. Actually, we can do it easier. If we shift to the left a number, it's like multiplying with 2. So if we take the previous number, like 21, and we multiply it by 2, because each one of these digits, this is 2 to the power 6, 2 to the power 5 instead of 2 to the power 4, plus 2 to the power 3 instead of 2 to the power 2, and 2 to the power 1 instead of 2 to the power 0, is basically like multiplying the previous value with 2. Next, 2 to the power 1, 0, 1, plus 2, plus 4, that's 7, plus 8, that's 15, plus 16, 31, plus 64, that is 95, I believe. We'll see in a second if I didn't miss anything. Let's try it. It's not complete, so we need to compute the last one. So up to here is 2 to the power 3, 8, plus 16 is 24, plus 32, 56. Okay, this one is incorrect. 32 plus 31, yes, it's 63. Any questions? we solved all of the questions in binary numbers. Yeah, so let's do this one more time. So the question is how to represent 1, 0, 1, 1, 1. That is 1 multiplied with 16 plus 0 multiplied with 8 plus 1 multiplied with 4 plus 1 multiplied with 2 plus 1. And that is 16 plus 4, 20, plus 3 plus 2, which is 23. Okay, so let's continue with the lecture. Hexadecimal to decimals. So the hexadecimal numbers have 16 digits, from 0 to 9, followed by A for 10, B for 11, C for 12, D for 13, E for 14, and F for 15. Given a hexadecimal number represented with these digits from 0 to F, which basically are each one of these digits, hn minus 1 is a digit, and basically ending with h0, the last digit has the index 0. Again, we start from the right hand side with the indices. We start with 0 as the first digit, and then 1 as the next digit, 2, and so on, incrementing with 1 with every position from right to left. The equivalent decimal value for that hexadecimal digit is hn, basically the first digit from left to right, multiply with 16 to the power n, plus hn minus 1 multiply with 16 to the power n minus 1, and so on up to h0 multiply with 16 to the power 0. That is the decimal value of that. So for instance, if we have the hexadecimal number 7f, that number is 7 multiplied with 16 to the power 1 plus 15, which is equal with 127 in decimal. It's usually quite difficult to do these transformations from hex to decimal directly, and we will see that in the case of decimal to hex we have to divide with 16. So for instance, another example is FFFF from hexadecimal is 15 multiplied with 16 to the power 3 plus 15 multiplied with 16 to the power 2 plus 15 multiplied with 16 to the power 1 plus 15 multiplied with 16 to the power 0, which is equal with 1, so the last term is in fact 15. Once we do all the multiplications with powers of 16, we get 65,535 in decimal. Octal numbers are similar, the base is 8, so when we do conversion from octal to decimal, we'll multiply with powers of 8 instead of powers of 16. Similarly, if we want to do decimal directly to hexadecimal, we will basically convert the decimal number d to a hexadecimal number to find the unique representation in hexadecimal hn to h0, where hn is different than 0, such that the digit d is equal with hn, the number d is equal with hn multiplied with 16 to the power n plus hn minus 1 multiplied with 16 to the power n minus 1, and so on up to h0 multiplied with 16 to the power 0. These numbers can be found by dividing 16 until the quotient is 0. So we start with 123, for instance, divided with 16. We get the remainder 11 and the quotient 7, and then 7 divided by 16 gives us the remainder 7 and the quotient 0. We read the remainders in opposite order as we found them, and that gives us the hexadecimal number corresponding to that decimal number. So the 123 in decimal is 7b represented in hexadecimal. Octal numbers are similar, but instead of dividing with 16, we divide by 8. However, in most cases, we are not doing directly division with 16 or multiplication with powers of 16. Why? Because we can do it easily by transforming the decimal number to binary, and then every 4 digits from the right hand side, grouped from the right hand side in any binary number, transforms into an exactly 1 digit in hexadecimal. So in order to convert a hexadecimal to binary, or vice versa, binary to hexadecimal, we simply convert each hexadecimal digit to the 4 digits binary number, or we group every 4 digits from the right hand side to the left hand side in the binary number, and we basically just see what is the mapping for that specific binary number in hexadecimal. So for instance, 0100 from hexadecimal is 2 to the power 2, which is equal with 4. So for every binary group of 4 digits, we have 1 hexadecimal digit from 0 to F. So let's take, for instance, an example. Let's say that we want to convert from binary to hexadecimal. We start grouping from the right hand side 4 digits. So it's 1101. 1101 corresponds to 4 plus 2 plus 1. 8 plus 2 plus 4 plus 1. 8 plus 4 is 12, plus 1 is 13, which corresponds to D. 1000 is 2 to the power 3, which is equal with 8, and 11 is transformed directly with preceding zeros, so it's 0011. 0011 corresponds to 3, it's 2 plus 1. So we can basically transform by just transforming groups or mapping the groups of 4 binary digits, bits, into one corresponding digit in hexadecimal. The other way around is done exactly in the same way. If we have, for instance, 38D, we transform D into 1101, that is the first group on the right hand side, 8 into 1000, basically we take the mapping, and then 3 into 0011, and we delete the preceding zeros, because like in decimal, any preceding zeros do not make any change to the number. Like for instance, 012 is still 12, it's preceded by 0. Octal to binary is done similarly. Instead of grouping 4 digits, we group 3 digits. So every 3 digits starting from the right hand side corresponds to one octal digit. So to convert an octal number to binary, we simply convert every octal number in the corresponding 3 digits, like 5 into 101, 1 into 001, and so on. To convert a binary number to an octal number, we group 3 digits at a time starting from the right hand side. So 101 corresponds to 5 in the mapping, 101 to 5, 001 to 1, 110 to 110 to 6, and 001 to 1. So basically we start from the right hand side and we convert the numbers. So let's go back to my programming lab and solve the next 3 problems in chapter Appendix F. So the first question is, what is the largest hexadecimal digit? The largest hexadecimal digit is F. We basically had from 0 to 9 and A to F corresponding from 10 to 15. Which is true about hexadecimal numbers? It is base 6? No. It is base 16? Yes. Using the first 16 letters of the Roman alphabet? No. It is base 16 and 16 is the highest digit? No. It is base 6? No. So none of those. Yes. The digit 5, hexadecimal 5, can be viewed as what sequence of binary bits? It has to be viewed as 0, 1, 0, 1. As I said before, preceding zeros do not change the number. So 5 corresponds to 1, 0, 1, and we put a 0 in front of that. The hexadecimal A stands for what binary sequence? First of all, A stands for 10, which is 8 plus 2, which in binary is 1010. It's 2 to the power 3 plus 2 to the power 1. Next two questions. What is 7 from hexadecimal to binary? So we can just look in the lecture notes. Basically, 7 corresponds to 0, 1, 1, 1. And to check ourselves, basically is 1 plus 2 plus 4, which is 7. The digit C stands for 12, can be viewed as what sequence of binary digits? We can do the translation from 12 to binary. So if we divide by 2, we get the quotient 6 and the remainder 0. 6 divided by 2 gives us the remainder 0 and the quotient 3. And 3 is 1, 1 in binary. The digit BB can be viewed as what sequence? So B corresponds to 1, 0, 1, 1. So now if we have 1, 0, 1, 1 for the first B and 1, 0, 1, 1 for the second B, we have the binary sequence for BB. AA is similar. So 1A stands for 1, 0, 1, 0 and the second A for 1, 0, 1, 0. Everything was correct. So now we want to translate from hex to we want to translate to hex this binary number. So 1010 stands for B, 1110 stands for 8 plus 4, 12 plus 2, it's 14, which stands for E. The next one is also the same sequence, so it's also E. The next one is F, because it's all the digits, then 2 zeros, and 1001 stands for 8 plus 4 plus 1, that's 13, which corresponds to D. We have to enter answers for all of them to check them. So 1010 stands for A, then 1011 stands for B, then 1101 stands for D, then 1111 stands for F, then 0000 stands for 0, and 1110 stands for 14, which is E. Next one, B, A, C, no, D, C, A, F, E. Last one, F, A, C, D, E, C, 1, C. Last one, let's do it again. FA 1101 stands for 12 plus 1, 13. Which is C. No. Okay, let's return back. One one zero one, 1101, it's D. So all of those C's are actually D's. Done. Any questions for conversions of numbers? Do you want to do more exercises of number conversions? You basically have unlimited number of times to submit all of your questions on my programming lab. In the end, I will download how many you solved correctly. So you basically have to start from the beginning and solve every problem one by one. What kind of devices are monitors? They are output devices. what kind of devices, what at each step, what does the central processing unit, it's a control unit, the input is an instruction, then a binary digit, it's either 0 or 1, so let's do that, and so on. You basically have to submit every question and continue with the next question and try to do them correctly. At the beginning there will be very simple questions. In fact, you can just choose one by one and try to see which one is the correct one. But later this semester you will have to do programming assignments in which you basically get you want to implement a program that prints a certain message. Like for instance here, you want to implement a program called welcome times 5 times that prints welcome to Java 5 times. So you basically need to write a code as the following: public class welcome times 5 that contains a main method, public static void main, that takes an array of strings. We'll learn all of this today, args, and prints that message 5 times. Every statement ends with a semicolon. We do it 5 times, after which we finish the program and the method. And my programming lab will tell you that everything you did was correct. Or if you have any kind of mistakes, my programming lab will find that there is a syntax error in that line, or there are other errors. Like for instance, let's say that we print 6 times the message, not 5 times. My programming lab will try to basically tell you that you displayed an additional welcome to Java different than the one that is basically required. So you need to basically correct your program to print exactly what is required and nothing more or less. So we are going to do all of this during the class today. Here is a much more complicated program that you have to implement today. Okay, so let's see if there are any more questions and then continue with the rest of the lecture today. Good. Any questions? Okay, let's continue. So when you run Java, it basically starts Java and actually uses multiple segments of memory. The ones that are most important that we are going to discuss about today are the following. The stack segment, it contains temporary variables declared inside methods. They are removed from memory the moment that the method terminates and returns. The heap segment, which is used for dynamic data, basically every time you are using the new operator, they contain objects that are stored permanently in the main memory. They are basically not deleted when you exit from methods. These objects are created when every time you actually use the new operator and you declare a variable of those objects. They are persistent as long as the object exists and there is a variable that points to that object, that refers that region of memory. And finally, the global segment of memory that is reserved during compile time for the program and static data, data that is linked to the class itself. Objects are stored in 2 different ways. Basically, you must understand that in Java, every object variable stores a memory address. A reference is basically an address, but you cannot have access to that address in Java. The numbers that can be stored, either in what version of Java you are using. If you are using 32-bit version of Java, it is using 4 bytes for every address, for every location in memory. And for a 64-bit machine or a 64-bit version of Java is using 64 bits for addressable locations in memory. These addresses point to the memory locations where the objects are actually stored in memory. This was important in the past for programming languages like C, where you actually can read and do pointer arithmetic with these pointers, with these addresses. However, in Java, all of this is hidden from you. So you do not have access to these locations directly. You cannot actually do operations, arithmetical operations with addresses. So the hardware stores 0 and 1s. The data is byte addressable. We can access any byte group of 8 bits independently. How do we store text? Basically, we use an encoding. Numerically, we can store the fact that first we store for the location that it's a text. The type of that location is text. And then we use the code. Each character is stored in memory as a number. And there are different encodings. ASCII is the original encoding. Basically, we have 127 different characters and their encodings in 7 bits. ASCII would use only 1 byte per character. For instance, the character A has the encoding 65. So instead of storing A, we are storing in memory the number 65 in binary. And here is a complete set. Basically tells us for the decimal number what is the character encoding. Basically for the character how is it encoded in the computer. So for instance, space is encoded as 32. 0 is encoded as 48. So the encoding, the way that the character 0 is stored in memory is actually stored as a number 48. And so on up to uppercase letters from A starting with 65 to Z ending with 90, and lowercase a which starts with 97 to lowercase z that it's 122. You don't need to remember any one of these basically encodings, because all that we care about is in fact the fact that we have a character. So we can represent the character in the program itself, like lowercase a within single quotes. That is the character for lowercase a. So programming languages evolved during time from a machine language, which basically is a set of instructions written directly in binary, executed by the central processing unit, to what are higher level languages today, like Java, Python, C#, and so on. Now, the first step was not actually higher level languages. First, programmers gave names, mnemonic names, like string names, to the binary instructions that are directly executed by the computer. So the computer would basically execute a sequence of bits as an instruction code and parameters to that instruction, but we can actually transform that sequence of bits into a mnemonic representation. Like for instance, add the first two registers R1 and R2 into the register R3. So these languages were still very low level, because all that they did were giving a name in English most of the time to binary instructions in the machine. So assembly was far easier to use than binary. Instead of programming with bits, basically writing 0 and 1s or a sequence of 0 and 1s, we were writing something that was closer to programming languages like add, subtract, load, and so on. However, they were not very friendly. Basically, you only had very low-level operations. Programming was very time-consuming. For instance, designing a graphical user interface was not possible, because you would have to load at every location of a pixel a certain value for the red or for the different colors available, RGB available for that location. So is not possible. You can't write a programming language or program completely in binary. So what people did, they basically wrote sets of such instructions. Like for instance, they would write an entire sequence of loading the every bit or every pixel on the screen, and then providing it as a method, as a procedure. So this actually started a new level of programming, higher level programming. It's more friendly, easy to use, flexible, platform independent. Basically, developers will develop libraries and other developers will use these libraries to implement their own algorithms. Popular higher level languages from the beginning of computer science were COBOL for bank operations, Fortran also for bank operations, but also for NASA and other big companies. BASIC started as a programming language in a university, but after that it was adopted by Microsoft for the development of their operating systems. Pascal was one of the most important languages developed basically in the world. C was basically the first programming language that was developed specifically for implementing large programs like operating systems, and then from C we evolved to C++, an object-oriented language based on C, and Java and C# and Python and so on. Now, most of these programming languages work as follows. You basically write the program into a text file called source code. Then you will compile that into machine level code. So the input would be higher level source code and the output would be assembly code, which is basically directly runnable machine level code, but with an output that is readable by humans. Is typically also integrated with an assembly that will link all the libraries together with the machine level file to produce an executable file for that specific platform. So you would take the source code, you will compile it like we do it in Java with Java-C. You would get a machine level language file that you will link it with library code, and then you will execute it directly on that machine. The operating system also basically adds another level to this to execution of programs, because it's a program itself that manages and controls the computer's activity, like file system operations. We don't have to implement an entire operating system from scratch, like how are files stored on disk, how are basically accessed, who is able to access various files, so user access control and so on. So, and there are different operating systems used in the world today. Windows XP was very popular, Vista, 7, 8, 10. Before those there was DOS, Mac OS X, Android, Linux and so on. The problem is that if a programming language is compiled in this way, you basically write the source code, you develop machine level files. If your operating system is different, it will have to basically compile differently and link differently the machine language file with the library code. So Java is a little bit different. It's not a compiler, it's not an interpreter, but it is both a compiler and an interpreter. The principle that Java employed from the beginning was that you write source code once and then you can run it everywhere. What that means is that it means that you have to be independent on the platform, both the operating system and the hardware. Doesn't matter what type of instruction set is adopted by your hardware, you should be able to run it everywhere. How is that done? It is done through the Java virtual machine. The Java virtual machine is an interpreter, type of machine that basically has a fixed set of registers, a fixed set of instructions, machine level instructions, but it is a level between the operating system and the machine, the real machine. So Java programs are compiled into this assembly language called Java bytecode, and the bytecode is executed in another level called the Java virtual machine, which is this platform-independent virtual machine that it's then ran on the real machine, on the real hardware. So for any Java program, in fact, when you are running it, you are not running it directly on the hardware. You are running it into a program that runs bytecode by bytecode instruction called the Java Virtual Machine, or the JVM, which is a program that runs the Java programs compiled and manages the memory for Java programs. The reason why is that they wanted to implement one programming language that runs on everywhere, on Mac, on Linux, on Android, on PC. Java can be also used in this case for web applications, like JavaScript does, to run programs in web pages like Java applets. Can also be developed for any kind of devices like handheld devices like smartphones and Palm computers. There were multiple versions of Java released during the years. The first one was released in 1995. JDK 8 was released in 2014. In 2016, JDK 9 was released, and this year in March, JDK 10 was released. There are also multiple versions, editions of Java. We are using in this class the Java Standard Edition, is used to develop client-side standalone applications. There is also an Enterprise Edition that is used in other classes like CSE114 at Stony Brook. It can be used to develop server-side applications such as servers, Java servlets, Java server pages. Our textbook uses the Java Standard Edition, which we are going to use in this class. So let's start with a simple program. A simple program like the one that we wrote earlier in Eclipse. I will show it to you now again. It is the program that we wrote a couple of in the previous recording, which basically prints "Welcome to Java," a simple message. First, we need to understand the anatomy of this program. We define a class. A class is basically a program in Java. The name of the class is welcome, which actually dictates that the name of the file that stores this class should be welcome.java. The same spelling. Java is case sensitive, so in this case we see that it's uppercase W followed by ELCOME in lowercase. The class contains a main method. The main method is the main entrance point for the program. It has the standard signature. It is a public, static, void method. It takes an array of strings as the input. Public is a visibility modifier. It tells us that this method is available to everyone in Java. Basically, it will be available to the command line to execute this class. Static means that is a method connected to this class. Is not a method invoked for objects instances of this class. A class in Java can also stand for a template to create multiple object instances of this class. Like for instance, a class person would stand for a template to define that every person has a name, an age, and so on. So for the moment, we learn these modifiers. Public means visibility public. Static means that it's connected to the class. Void means that it does not return anything. The return type for this method is nothing, void. The parameters within the method definition, main is the name of this method. The parameters is a list or an array of strings. And then we have a block, and in this block, which is basically the beginning and the end of the curly brace. And within this block, we have the sequence of statements that will be executed when we run this program. In this case, the statement welcome to Java, print welcome to Java, that prints this message in the command prompt or the console. So if we would write this program from scratch. That means that we'll open our favorite editor like Notepad, we'll write this program, we will compile it with Java-C, we will save it on in a file welcome.java, we'll compile it with Java-C, the output will be bytecode, basically an executable file on the Java virtual machine that can be executed with the Java command. Basically, we can run the JVM, pass in the bytecode, and we'll see the result of this program. All of this can be done, as I said, if we actually write the program in an editor, any editor we like Notepad, Emacs, VI, and so on. But we can do exactly the same thing, but not running the programs from command line, but writing it in an editor like Eclipse. In Eclipse, we basically create a project like we did it earlier. We create a class and we write the code into this class. If you want to run programs from command line, you can basically use your favorite editor, like I'm using Emacs in this case. Then you compile the file and you run the Java bytecode with the Java command. You can compile and run Java from the command window as long as Java is accessible in your path environment. Basically, the environment variable should contain a path variable which basically points to the Java executables. If you need help with setting up the path so you can run in the command line by default Java programs, we'll also do that in a second. So in fact, let's try to do it now. CMD is the main command prompt in Java in Windows. Java is available by default. Java-C is not available by default. So let's add it to the command line. So first of all, we need to find where Java is located on your computer. So let's try to run Java. We are going to open that location so we can actually find where is it. In program files, that's program files, Java, JDK1 bin. Let's take this link, edit our properties of our PC, open the environment variables, find the path variable, add a new location which is in that bin directory. And since that doesn't work, we are going to edit the other one, the user one, and now Java will be available in the command line. Yes, and the version that we are currently running is 10.01. Good. So that is how to set up the JDK path in the... You don't need to do it, at least I don't think that you need to do it, but I just wanted to show it to you. Now, how do we run a program? We can run it in the Eclipse as we did it in the previous recording, and we can also trace it in Eclipse as we did it in the previous recording to print out messages. So we'll talk now about the anatomy of a Java program. Basically, what are the parts of a Java program? We'll see the different type of commands that we can write in Java, reserved words or keywords, basically words that have a predefined meaning, modifiers or visibility modifiers like public, private, protected, static, statements. Every statement in Java is an instruction that gets executed most of the time in one cycle, but not always. Blocks, which are basically how do we actually group together a sequence of statements. They start with curly brace, they end with curly brace. Every variable declared in a block is available for use between the point that it was declared up to the end of the block in which it was defined. It's also available inside inner blocks. So if you define an inner block within a block, a variable that was available before entering the inner block is also available in the inner block. Classes are programs in Java. Basically, they have two meanings. One is that they are programs. The second meaning is that they are also templates for defining objects, instances of that class. We are going to talk about that in the second half of this semester. Methods are sequences of statements that are executed under a single name. So for instance, you want to compute an average. For that, you need to sum the elements of the structure and then divide with a count. You can put this code that does all of these operations in one method with the name average that has a set of parameters, and every time you invoke that method with different parameters will compute the average of that set of parameters. One method that is special is the main method. The main method is the main entrance point of a program. When you run from command line or in Eclipse a program, the method that gets executed from this program is the main method. So today we are going to talk introductory about all of these issues. So we'll start with comments. There are three types of comments in Java. Line comments is basically a line comment preceded by double slash. They are ignored by the Java compiler and the execution of Java. They are only used to basically have a message for a different programmer or for ourselves in the future what the next line or the current line is doing. Paragraph comments, they are enclosed within slash star and star slash in one or multiple lines. And Java doc comments. Java doc comments begin with double star or slash double forward slash double star and end with star forward slash. They are used to document classes and methods. They can be extracted into one HTML file using the Java doc command. So let's see. In this program, we basically had one line comment. You see, if we double click, we have one line comment, we have a Java doc comment, and we may have other comments. Like for instance, here we can add a comment saying that then we print twice some text. So one thing that you can do with this project is to collect the Java doc for this project. Generate Java doc. This will generate, as we saw in the previous case, for all the Java doc comments. Let's configure it. We need Java doc. Here we need to generate basically the documentation. Let's name this my documentation. So we generated HTML code that completely basically talks about my program, my package. So in this case, there is a main method, and this main method has the main method is the main entrance point for the program. So the Java doc was actually collected in this HTML page, which is a web file. Okay. So comments are three types of comments. They are ignored by the compiler and the interpreter or the JVM, and they basically only contain notes that we want to make to our future selves or other developers of those programs. Then there are reserved words or keywords. They are words that they have a specific meaning to the compiler. They cannot be used for other purposes in the program, like for instance class. The word after class is the name of the class. We cannot use class for a name for a variable or a name for anything that we are actually using in our program ourselves, user-defined words. These are all the words available as keywords in Java. You cannot use them for other purposes but the ones that were designed. Abstract is for defining basically classes that are abstract. You cannot create instances of these classes. Assert are for assertions, basically checks that you want to make during execution, and they have to be true. Boolean is a type. There are 8 primitive types in Java. We are going to talk about them the next lecture notes, basically the next class. Break is a statement in Java that is used to break a loop. Byte is another type in Java, and so on. We will slowly during this semester we'll learn the meaning of all of these keywords. Modifiers are certain reserved keywords which specify the properties of data, methods, classes, and how they can be used. Who can use different methods. For instance, public, private, and protected are visibility modifiers. A public data is available to all the classes in any package. A private data is only available to methods within the current class. No one else can actually modify private data but the current class methods. In a similar way, we'll talk later about protected. Protected means that data that is protected is available to subclasses, no matter in which package they are, and the current class. No one else can access data that is protected, but subclasses or classes in the same project or in the same package, or and that's it, or the current class. Similarly for methods. Methods basically can also be public or private. Final data are basically data that cannot be modified. Final is a keyword that is used in front of ID definitions like constants or methods that cannot be overridden by other more specific implementations. A statement represents an action, or if a statement is a method invocation, a sequence of actions. Like for instance, system.out.println welcome to Java is a statement. Every statement in Java ends with semicolon. So in this case, in fact, println is a method that belongs to this output stream, system.out, and that method will print the string welcome to Java in the output stream. If we have multiple statements or multiple methods that belong to the same block, for instance, we want to define multiple methods within the class test, or we want to define multiple statements within the main method, we can use blocks. A block is a pair of braces, open and close braces in a program that forms a block and groups the components of the program. For instance, a class block starts after we define the class and ends when we finished all the methods for that class. A method block starts when we define a method, and basically it contains all the statements that are executed when we invoke that method. Now, even within methods we can have blocks. These are basically inner blocks. They are blocks defined within the outer block. They are also to group components within that inner block. There are two types of blocks. These are a matter of style in Java. The end of line style is the one that is used by modern programmers and Java preferred style of programming. Like for instance, if you use the formatting tool in Eclipse, you select all your text and then you format your source code, it will use the end of line style, which basically puts the beginning of the block at the end of the line of the current block definition, like for instance public class test. The next line style is basically a style where you can align the end of the block with the original beginning of the block. It was and it still is a style used by programmers, especially from C, to define methods that can be traced easily, basically where is the beginning and where is the end of the block. The problem that I find with programs that are using next of line style is that they are a little bit longer than programs that use the end of line style. So that's the reason why most programmers today prefer the end of line style. But in this class you can use either. I personally prefer the end of line style, but we will not grade you on the style of your program. We will grade you on the correctness of your program. Now, when we write a program, we actually define an API. API stands for Application Programming Interface. It's the set of all the variables, classes, and method names that we define, the user defines. It's basically a library of the code that can be used out of the program. So we can use names in Java and many other programming languages for variables, classes, methods, anything that we need to access, we need to basically name so we can address it later. And these names come from two sources. Our own classes, the set of all the names that we give to variables, classes, and methods. It's also called the referencing environment. What is everything available in our program at any point in the program? The referencing environment at that location. Or they can come from somebody else's API, like Oracle, or before Oracle, Sun, or Apache, or any other API that we may use in our program. So how do we name our variables, classes, and methods? We are basically using mnemonic names like my variable, or circle, or radius, or person, or even Paul. So we can declare variables, and we'll see how to declare variables later today. We can basically define my variable is a variable of the type integer, and we assign the value 5 to it. Then we can use those variables later to compute a value like my variable plus 1 and assign the value to itself. So we basically modify, increment that variable with 1. But before we do that, how do we name things? Basically, what are the rules what are the characters that we can use in identifiers? We can use letters, digits, and underscore. $sign is also allowed, but is used for special purposes. Basically, it will be added by default by Java when we define an inner class. It will basically say that this inner class is defined within the outer class, and it will separate the class names with the $sign. We cannot begin with a digit. Uppercase and lowercase letters are considered to be the same characters. For instance, my variable, my underscore variables, my for variable are all correct legal variables, identifiers. For my variable is not a legal identifier because it starts with a digit, and we cannot start with a digit. We must start either with number or underscore. My space class contains a space, and the space is not allowed in identifiers. My exclamation sign or the @ sign and all of these are not actually allowed in identifiers because identifiers may only contain letters, numbers, and underscores and do not start with a digit. Then there are also like styles, common naming notations, conventions in Java. So for instance, variables and methods start with lowercase letters. like lowercase x, or toString, it starts with lowercase t. Classes start with uppercase letters, like for instance person starts with uppercase. Variables and class identifiers should generally be nouns. Method identifiers should be verbs. And if we have multiple words within one identifier, like my variable, my class, we should use what is called a camel case notation. Camel case notation means that every word in our identifier is capitalized. So my variable with uppercase V, because there are multiple words, and when we have a word transition, we should capitalize the first letter in that word transition. Similarly, if we have a class, classes start with uppercase, and since we have two words, my class, we will capitalize M and C. So it is like a camel. We have these humps for every uppercase letter, my variable, my class. Although it is legal, do not start with underscore. Basically, it's conventional not to start with underscore. This is different than Python, where there are actually methods that start with underscore, like init, str, eval, representation, and so on. In Java, we use underscore within a variable name, but we do not put it at the beginning of the variable name or identifier name. Also, for your own readability, use descriptive names. Like for instance, specify exactly what do you have in that variable or that identifier. You have a linked list, call this class linked list. A method that compares two objects is called compareTo. An area in a variable, a constant for the value of pi, or a variable for the radius of a circle should be named area, pi, and radius. Now, before we continue, in order to understand what exactly are we doing when we program large programs, we have to learn the different types of errors in Java and any other programming language, as a matter of fact. Like for instance, we have to make the distinction between syntax or compiler errors, runtime errors, and logical errors. Logical errors which may actually not always terminate in some error that is detectable by the compiler or the executor, but actually they produce incorrect results. So syntax errors, they are errors detected by the compiler. We basically forget to put semicolon at the end of a line, or we use a variable before we declare it, or we misspell a keyword, like instead of public we may write private. Well, that's not probably a good example, but basically there are misspellings or errors of syntax in developing the program. Runtime errors, they are errors which syntactically they are correct, but which may cause the program to abort because the operation that they try to do is illegal. Like for instance, we can have a division. A number divided by number, in most cases, returns another number, except when you divide by 0. When you divide by 0, the result of the division is plus or minus infinity. 1 divided by 0 is infinity. But that cannot be represented. We cannot represent infinity as a number on 8 bits or 16 bits or the number of bytes allowed for that specific program. So in that case, that is an error that will basically crash the program. It causes the program to abort abnormally, and we can either correct the error in the program or actually catch that exception, that specific error. Finally, logical errors is when we implement a program, but that program is not implementing the description or the requirements of that program. Like for instance, we want to detect if a number is between 0 and 100 included, and we don't. We actually return for 100 that is not within that interval. So here we have examples of each one of them. For instance, this is a syntax error. If you try to define a variable and you assign a number to it like I equal with 30. We will see in the next recording how this is done properly. It will actually be detected by the compiler. That is a syntax error. You cannot assign a value to a variable if you don't specify what is the type of that variable, because the type specifies in fact what is the location, the size of the location of memory to store that value. So in Java and most of the strongly typed languages, you have to define the type of every variable, so it knows exactly how much space to allocate for that specific variable. Runtime errors are again errors which are syntactically correct. So here it is correct syntactically that we assign to an integer divided with an integer. That in most cases, except when we divide by 0, it actually returns the quotient of the division. However, if we try to divide in this case by 0, the result is infinity, which cannot be stored. It's infinite number of digits. So basically, we cannot store it, therefore it will crash the execution during runtime. And finally, logical errors. Logical errors is when we implement a program, but that program does not actually implement what the requirement was. So for instance, in this case, we will actually talk about this in the future, in a future lecture. We basically check if a number is between 1 and 100, including 1 and 100. But the condition that we wrote below checks if the number is strictly greater than 1 and strictly less than 100. So we will get wrong results if the number that was entered by the user in the command prompt is actually 1 or 100. It will tell us that the number is not between 1 and 100, including 1 and 100. So this is not an error. It will not crash the program. It will let us run it. It's not a syntax error, but it implements a different problem. So the result is wrong. This is called logical errors, and it's very hard to catch logical errors because either they were implemented correctly from the beginning, or we are testing the program with all the possible inputs. Most of the time, users have to test their programs with the edge inputs, like for instance 1 and 100, probably also 2 and 99, and also -1 and 101. So you basically try all of the possible values that would give you a possible logical error, and then you decide that this is a correct implementation or incorrect implementation, and you fix it. That process is called debugging. So logical errors debugging are basically to catch these logical errors. These logical errors are also called bugs. Therefore, the process of finding and correcting them is called debugging. And there are multiple methods to do it. One is basically reading the program by reading the program and hand tracing the program. Another way, which is preferred by some programmers, is to insert print statements in the program, and then you would see at every line what the program prints. I personally would basically tell you not to do that, because most people forget to take out the print statements, and they will actually print a lot of garbage during the execution. So large complex programs should be debugged using a debugger utility, like the one that we saw in Eclipse. It's a program that executes statement by statement, one statement at a time. It traces into methods and stepping over methods. It allows you to set breakpoints. It would display the variables available in that specific method. It will display the call stack, basically what method we are currently executing and who called that method. It will modify the variables and so on. In fact, you can even modify variables like, oh, so what would this method do if we modify the value of I from 7 to 11? So you can actually modify the stack yourself. And as I showed you earlier, you can put a breakpoint. You can set a breakpoint by double-clicking on the side of the program. on this side of the program, and then click on the button for debugging, which will basically open the debugger in which you can step into a method, step over a method, or exit a method, and you execute the program line by line. One of the tasks that you have to do today is to execute the program with the debugger and return back to the Java perspective. So there are different perspectives. You see, this is Java and this is the debugging perspective. You can change between those perspectives in Eclipse. At this point, we are going to stop the recording for the introduction to computers, programming, and Java, and we'll respond to questions, after which, if we have time, half an hour, we'll continue with the next topic, which is elementary programming.